Hello everyone, this is Lecture 6 of CAMsci 174, Motion Detection and Tracking. In today's video, we will discuss two video analysis tasks, namely motion detection and tracking. In motion detection, we will be looking at background subtraction and different background models. For tracking, we will also discuss the related task of optical flow. Okay, so let's start. So, in motion detection and tracking, we will be working with videos, and videos are just a sequence of images. So, when we refer to individual images in the video, we usually call them frames. In an image, it's usually static, right? There's no movement. So, it's a still image, so it's only static. But in videos, it's usually dynamic and they display object movement. Okay? So, for example, if you have a video of this jockey riding the horse, then it would display the movement of the horse galloping on the yard, right? So, the video here is made up of different frames that we extracted one by one, okay? So, that's a video. Usually, we need to know the frame rate of the video, which is the frequency of displaying images. So, the frame rate will dictate how fast you change from one image to the next, okay? And we usually measure this in frames per second, or FPS. And the common frame rates are 24 FPS, 25 FPS, 30 FPS, and then you also have the 60 FPS, okay? So the more frames per second, usually the bigger the file, because obviously you need to store more images in the video. But you have to use the appropriate frame rate to make the video look seamless. The motion in the video looks seamless, because if not, like if you only have like 10 frames per second, then the video will look choppy, okay? The movement will look very stop and go, right? So this common frame rates will usually assure that the motion in the video will look seamless, okay? So yeah, that's frame rate. Now, we usually distinguish between video files and video streams. In a video file, of course, you have the start and the end of the video because it's a file, right? So you can go jump to a specific frame in an instant, okay? So you have control over all of the frames already because it's a file, right? Whereas in video stream, you usually don't have that control, okay? So you can only look at the current and past frames. You cannot look at future frames because, of course, the video stream is like ongoing, right? So it's a ongoing stream of images, so you cannot look at future frames, okay? So we need to distinguish between these two because later on, when we have like video streams, it might be difficult for us to do some background modeling, right? Because you don't have control of the whole video yet, okay? Next, we also need to distinguish between a static camera and a moving camera. So usually when we talk about static cameras, then they are in place, usually let's say in a tripod, so they're not moving, okay? So it's a still camera, and of course the opposite is the moving camera. Maybe it's handheld, or it's in a tripod but you're moving it up and down, or yeah, you're moving it around. So basically when we say static, you are not moving it, you don't pan or you don't rotate, right? You don't tilt, and you also don't zoom in and out, okay? So basically you only have like a stationary viewpoint, okay? It doesn't change throughout the video. Whereas if there is already a change in the viewpoint, then that's already considered a moving camera, even if the camera itself is not moving, but the tilting and the panning, that is considered movement, okay? So yeah, we have to distinguish between these types because later on we will come back to this and say that in some instances it might be difficult for us to process videos from moving cameras, okay? so we might assume that the video comes from a static camera. Okay, so those videos. In OpenCV, I've listed some of the relevant video functions and properties. So to open a video file, you usually use the video capture function, and then you pass in the path of the file. If you want to use the camera, then you pass in integer, which is the index of your built-in cameras or other cameras that you added. So if you have multiple cameras in your computer or attached to your computer, then you can access them through their index. So 0 being the first one, or the built-in 1, maybe if you have a USB camera, then you can access that as well. Okay, if you want to save a video, then you use the video writer class. Okay, so look it up if you want to. And then the others are properties that you can get for a video file. So you can get the property like the frame width, frame height, the FPS, the frames per second, frame count, so the number of frames in the video. Position frames refers to where you are now, or maybe like the frame index. Okay, so if you're at the start, then that would be frame 0. If you go to the next frame, that's frame 1, and so on, all the way up to the end. Okay, so position frames will tell you where you are now currently. So if you are reading the video for frame per frame, then this will tell you your position. Position millisecond is kind of similar, but not in terms of frame numbers, but in terms of well, milliseconds. Okay, so where are you now time wise? Okay, so maybe if you're in 1 second, then that's 1000 milliseconds, and so on. And then position of AV ratio is somewhat similar. It also tells you your position in the video, but this time this will give you a value from 0 to 1, and 0 will be the start, 1 would be the end. Okay, so it's like 0% to 100%, and then if let's say you pass in 0.5, then that means that you're halfway through the video. Okay, so you have different position types, like in terms of frame number, in terms of seconds, in terms of like percentage of the video. Okay, so you can use this properties and functions for your video processing in OpenCV. Okay, now there's a lot of video sources that we have. So for example, we can get videos from CCTVs for surveillance, like this one, and let's say traffic videos. Okay, so you have CCTVs also installed along major highways and major streets, so as to monitor the traffic, right? So that would be another source of video feed. Of course, your dash cam videos in cars. So for example, if you have a self-driving car, then obviously that will have a sort of camera attached to it, so that it's able to see the street and then the obstacles and the pedestrians along the way, right? So that's another source of video. And then you also have video sources coming from factories in manufacturing, like for example in quality control. So you can have a bot or a robot that will monitor the quality of the, let's say for example here it detects a bottle cap that is slightly it's not right. Okay, so it doesn't pass the quality control because it's slightly how do you say this, bent, I guess. So this will have to be discarded. Okay, so that's another source of video. You also have things like in agriculture, you can have drones take like a drone shot of your plot of land, and then you can do that to analyze your farm basically. Okay, so you can also do that. And then also in fisheries, so you have things like visual fish survey, or like visual fish survey, fish census. Okay, so you're basically trying to identify and count the number of fish species in a certain site, basically. So the person in this video, the diver here, is actually my former advisor in grad school. He was the one who was leading this project, wherein we create a rig consisting of GoPros attached to it, and then the GoPros will kind of capture the fishes that will pass by, and then you'll analyze the video to count and identify the fish species. So something like that. Okay, so that's another video source. Of course, you also have things like sports videos. You can analyze the movement of the players and their strategies. And of course, from your webcam and personal videos, that's also another source of video. Okay, so there's a lot of sources for videos. Now, what can we do with these videos? Okay, so how do we analyze them? So there are three main tasks in video analysis. Of course, there are more, but these are the three major ones. So you have your motion detection, object tracking, and action recognition. So in this video, we will discuss the first two. We won't cover action recognition, but basically action recognition is, well, how it sounds like. You're recognizing actions in the video. So for example, if the person is diving or swinging the doing a golf swing or kicking or lifting and so on, then you can recognize those actions in the video. Okay, so that is also another task in video analysis. A related task, not necessarily for videos, but you can do this for still images, is something called pose estimation, wherein you're trying to well, estimate or model the pose of a human, and this will help you recognize the action later on because you are estimating the pose, and that will tell you more or less what the action the person is doing. Okay, so that is action recognition. But as I mentioned, we will focus on the first two tasks, which are motion detection and tracking. Okay, so let's start with motion detection. So in the video, you usually have two parts of the video. You have the background part, which is the static part of the video. It's the one that doesn't move. And the foreground is the dynamic part of the video, wherein the objects in the foreground are changing, they are moving. Okay, that's why it's dynamic. And in motion detection, your goal is to segment or separate the foreground from the background. Okay, so you just want to extract the foreground part. You want to extract or get the moving part of the video. So that's why it's motion detection, right? So the foreground will show the motion of the moving objects. So you want to subtract the background to detect motion. Okay, so that's why background subtraction will be what we will do to do motion detection. Okay, so for background subtraction, to get the foreground, we have the image, and then we'll subtract the background. Okay, because the image is basically just the foreground and the background, right? So if you want to get just the foreground, then you subtract the background. Okay, so simple as that. You can do this in OpenCV by using the absdiff function. So you pass in the frame and then the background frame, and then if you do absdiff, then it will take their difference and apply absolute value, just so you don't have negative values. Because what if background frames pixel value is higher than the frame's pixel value? So it might be negative, right? So we don't want that, so we just take the absolute value. And then after getting the difference of the frame and the background, we usually threshold the difference image, and this lets us detect the pixels with significant difference from the background. So basically, you want to threshold the difference image. So let's say your threshold is set at let's say 50. Okay, so if your threshold is 50, you are saying that the difference that are less than 50, so let's say mga 10, 0 or 1 or just 5 or 20, those are all less than 50. So those will be negligible. Okay, those are negligible differences, and we can just let that one go. So only those that are greater than the threshold will be considered as part of the foreground. Okay, so we threshold, and then after that we could also post process the result to improve it. Okay, so yeah, that's background subtraction. Now, um, before we can get the difference of the images, we have to consider that usually these frames or these images are colored, right? So they have 3 channels. So if the frames are colored, what we usually do is either convert frames to grayscale. So the frame itself and the background frame will be converted to grayscale before we take their difference. Or we could process each channel. We take the difference in each channel and take the maximum or average difference. Okay, we can also do that. Or you can also just focus on certain channels. Like let's say you just look at the hue channel in the HSV color space. That's also possible. Okay, so just consider this because if you are just just going for the difference right away without converting it to grayscale first, you will get a difference image, but it's also still having 3 channels, and you can't use that for the mask. Okay, so the mask has to be a single channel image, okay, a grayscale image. So yeah, that's something you need to consider. But let's say that we are converting it to grayscale. So let's say that this is the one that we chose. So assuming frames are grayscale or at least 1 channel, then we will get the difference image by using absdef, as I mentioned, of the frame and the background frame. And then we'll threshold using the threshold function. That will let us produce the mask. Okay, and the mask, as you know, is a binary image wherein your values are either 0 or 255. Okay, black or white. If it's black, then that means that that pixel is part of the background. If it's white, that means that that pixel is part of the foreground. Okay, so your mask here will tell you which part of the image is the foreground. Okay, so those will be signified by white pixels. Okay, so that's the difference image. Now, in your difference image, of course, there's true positives, like the white ones that are actually foreground. Okay, so those are correct foreground pixels. True negatives are the correct background pixels. But you can also have false positives. Okay, so you are showing it's supposed to be part of the background, but you are showing it as a white pixel. So that means that it's just noise. Okay, it's not supposed to be white because it's supposed to be background, but you're showing a white pixel there, so that's a false positive. And then the opposite, of course, is the false negative, wherein it's supposed to be a foreground, but you are showing it as a black pixel in the mask, so that means that you're not detecting it as part of the foreground. Okay, so that's a false negative. Okay, so of course we want to have as many true positives and as many true negatives as possible. Okay, so that's difference image. So it would look something like this. The first one here, the top left, is the frame. The top right is the background frame, and then the bottom right is the difference. Okay, so if you subtract these two together, then you will get the difference, which is right here, the person. Okay, so let's label those. Maybe blue, I guess, will be visible here. So you'll notice here that this person is not part of the, okay, maybe red is more visible. Okay, so this person here is not part of the background, right? So it's being detected here. And then this white van here is also not part of the background, right? So that's also part of the difference right here. And this car right here, this newly parked car, was not part of the background background model, so it's also detected as being part of the difference. Okay, so it's also being detected as movement, because it's not, if it's not in the background, then that means that you are a foreground object, so that's also being detected. Okay, so yeah, that's a difference image. So it's really reliant on the background frame itself. Okay, so you can also apply morphological transforms to clean up the mask, because as you can see here, there's a lot of like noise, right? Small dots right here. So you can apply morphological transforms like erode, dilate, and so on. Morph open, morph close. You can also adjust the threshold to improve the foreground. Okay, so if you have a low threshold, it tends to be noisy. The mask tends to be noisy because since you're setting a low bar, then you're allowing even small differences to be converted into white or converted into foreground. So you end up with a lot of detections. Okay, and your mask tends to be noisy. But if you have a high threshold, then your mask will be somewhat limited. Okay, you will be left with few detections because you're setting the difference to be to reach a high threshold. So kind of looks like this. If your threshold is low, then you will have a lot of this noise right here. Okay, but if your threshold is high, then there won't be a lot of noise, but the car here, you'll notice the mask is not really full, right? Because it's missing some pixels on the top part. Okay, it's incomplete because you are setting a very high threshold, and the pixels here supposedly were not able to make the cut. Okay, so that's the effect of the threshold. Okay, so before we can do background subtraction, we have the frame from the video, but where do we get the background frame? Okay, so to get the background frame, we need to have some sort of background model. Okay, so for the background model, we will need to assume that we are using a static camera. So meaning it's not moving, it's not panning, it's not zooming, it's not tilting, and so on. So it's really just stationary, not moving at all, just one viewpoint throughout the whole video. Okay, because if we have a moving camera, that makes it harder to model the background, because besides the movement of the objects itself, your camera is also moving with the objects, so it kind of makes it hard to model the movement. It's hard to distinguish between whether the movement was because the object was really moving or because the camera was moving. Okay, that's what I mean. So let's just assume that we're using a static camera, and otherwise this background models will not work as well. So the background model will just estimate the background image. So we want to have a background image, but it's hard to get this actual background image. Besides, it also kind of changes through time, so it might not be a good idea to just have one, right? So instead, we will have like a model to estimate our background. Okay, so as I mentioned, the background could change over time, so we need to consider this, and we need to also update the background model so that it doesn't stay with the current background even if the background has already changed, right? So we'll discuss what these changes are in a while, but be aware that the background could change over time. So for example, due to lighting changes, or if you're doing a time lapse from morning up to afternoon, of course the background model will change because of lighting conditions or the clouds, or if you're looking at the parking lot, then cars will come and go, and that changes the background model as well. Okay, so there's a lot of possible changes to the background that you need to consider. Okay, so motion detection using background subtraction is reliant on the quality of your background model, because if your background model is terrible, then of course you cannot expect your background subtraction to also work well and detect motion. Okay, so you need to have a good quality background model for your motion detection to also have good results. Okay, so let's start with the easiest background model, which is the static background. Okay, and it's just a static image of the background. As I mentioned, this is hard to come by, or it's hard to get the actual static image of a background without like any moving objects, because we might not have it. And if we don't have it, or if you have it, then well, good for you. You have a static image, so you can use it right away. But if you don't have it, what you can do is you can use the video's first frame, but you are doing a very big assumption here. You're assuming that the video's first frame does not include any foreground objects. Okay, and usually this is not the case, because at the start of the video it could be that people or cars or other moving objects are already there. Okay, and if you use the video's first frame as the background, then the results will be not as good. Okay, so we'll see this later in the demo, but yeah, that's the basic idea. If you have a static image of the background, then use that. If you don't, you usually use one of the first frames of the video. It doesn't necessarily have to be like the first one, but usually near the start, when you're assuming that no moving objects are yet visible. Okay, so of course this is not very robust to background changes over time, because it's a static image, so you only have one model of the background for maybe a long period of time, so it's not very good. Okay, so changes to the background like lighting, or if you add and remove objects, if for example you have like cars that are parked, so maybe at the start it was a parked car, so it was assumed to be part of the background, but then the car moved out of the parking lot, so the car is not there anymore, so it should not be part of the background anymore, so you need to update that, right? So if you only have a static background, of course it's not it does not cater to these changes. Okay, so yeah, it's very limited to what it can do. But if you have a good background image, then well, good for you. So for example here, if this is our background image and this is the frame, the difference will actually detect this white van here, because if you take the difference of this and this part here, then the white van is obviously missing, so it will detect motion here like a ghost part, right? And of course the red car here is also present. It was not present in the background, so that will also be part of the movement. And then the newly you have the so let's annotate that. You have this one here is missing from the frame, right? So that's right here. And then the red car is in the frame but not in the background, right? So that's also part of the difference. And then you have a parked car in the background right here, but in the frame it's missing. It's not parked there anymore, so it will be also part of the difference. Okay, so that is the limitations of static background. Okay, so next model is using previous frames. So what we mean by this is we'll treat the previous frame as the background. Okay, so since we don't want static background frames, then maybe we can update the background frequently. Okay, now this one naman is going all the way to the opposite extremes, right? The static background is never changing. This previous frame model is always changing, right? Because in the next frame you're using the frame now as the background, and in the next frame you're using the frame the previous frame again. So it's always updating. Okay, so you detect motion if the pixel values change from previous to current frame. So the background model changes in every frame. Okay, so yeah, it could be something like this. So to us it might look like these two frames are similar, right? But there is a slight movement from frame 1 to frame 2, and that will be detected by applying the difference. Okay, so yeah, that's previous frames. Now if you don't want a continuous update, like per frame update of the background model, you can do something like the running average model. So for the running average, you maintain a running average of previous frames. Okay, so how will that look like? So let's say that this is your video clip, and let's say that this is currently your frame right here. So you're here. So you look at a window of like a certain size. So maybe I'll use a different color, maybe blue. So you look at a window of previous frames and get their average, basically. So get the average of this previous frames, and that would become your background model. Okay, so in the previous one, in the previous model, we had like something like this. Okay, wherein the previous frame itself is the background model, right? And then if you move to the next one, like if this is now your frame right here, this yellow frame will be the new background model, which is the previous. But in running average, what will happen is you kind of maintain a running average of the previous frame. So for example, if you move on to the next frame, then it would kind of look like this. So it would look at the next window of previous frames, basically. Okay, so yeah, that's the basic idea. You can control how the new frames are added by using a learning rate. Okay, so since you're updating this running average, new frames will be added to the background model, but you can control how they are added. So if you have a small learning rate, then the new frames can only contribute a little amount to the background model, so the older frames will mostly form the background. But if you have a large learning rate, then you are relying a lot on the new frames to make up most of the background, and you forget a lot of the older frames easily. Okay, so newer frames mostly form the background if you have a large learning rate. Okay, so you can experiment on the learning rate to see how well you update the background model. Okay, so we'll also see an example of this in later on in the demo. So running average now takes into account lighting changes, because for example, if in your, let's say in your clip, okay, like for example in this part here, maybe it was sunny, okay, but at this part here, maybe it was like cloudy, right? So if you look at if your frame is currently right here, it will look at the previous frames, then it would be maybe sunny, right? It would look at the sunny background. But if it's somewhere here and it look at the previous frames right here, then it would look at the cloudy background. So it would take that into account and update the background model. Okay, so you can now have different background models depending on where you are in your video. Okay, because you're looking back at a certain window from previous frames and getting their average. Okay, so yeah, so you're accounting for lighting changes. And the downside, however, is you're also incorporating moving objects into the background because you're still looking at previous ones. So they might be included in the computation of the background model. So we'll also see this later in the demo. You can do this in OpenCV using the accumulate weighted function. Okay, so you can do that to accumulate the running average model. Okay, so we have a example screenshot here. So this is the frame, this is the running average. So from the running average you get like a clean background. This was converted to grayscale, and then if you get the difference, then you have like a clean mask of where the difference is, like mainly this white van here, right? So yeah, that's running average. Now next, you can also do mean or average from sample frames. So how will we do this? Okay, so instead of looking at the local the previous frames, okay, what we can do is we could sample a few random frames from the video, and you can do this by, let's say, jumping X frames at a time and compute the mean of the sample frames. So how will that look like? Let's say this is your video. Okay, so this is your video clip. Okay, so let's say that you have maybe 1000 frames in the video, and maybe I want to get let's say 50 sample 50 frames. So what I can do is so 1000 over 50 is how much? 220, right? Tama ba? Is 20 the right answer? 20 times 50 is, yeah, it's 50. Sorry. Okay, I just had to make sure. So 20 skip. So your skip will be 20. So every 20 frames, so since you have 1000 frames and you only want 50, then you will have to skip 20 frames at a time. So maybe you will get you can sample this one, get this one, and then you jump 20 frames, and then you sample again, you get this one, jump 20 frames, then sample this one, and so on until you reach the end. Okay, and so you get 50 frames that way. Okay, and then from those 50 frames that you had, you compute their average. Okay, so you get the mean of the sample frames. Okay, does that make sense? So how is this different from the previous one? Okay, in the previous one, in running average, what you were doing was you were looking at like a small window, small local window, right? Which was your previous frames basically. So if this is where you are, your window right now is just like here. Okay, previous X previous frames. But in sampling from sample frames, you're actually doing this in a global like window, because you are getting frames from here, from here, from here, from here, from here, and so on. Okay, so you're not just getting frames from a local window, you are getting it from everywhere in the video. Okay, so that makes it more global, more robust to the whole video. So yeah, that's what you do. And instead of doing mean, you can also compute the median. Okay, so mean and median are of course your trying to find the center of a data set, right? So average or median works well for either one works well. So as I mentioned, this looks at a global window of frames, not just a local window like in running average. Okay, so for example, here you have a median from sample frames. You can compute that and get like a clean background image from the median, and then if you take your difference, then you get like a clean mask here, like the white van, the person standing here. So I don't know if you can see, but there's a person standing here trying to get into the car, and there's also a person walking here, somewhere here. So those two are detected in the difference. Okay, so you can do that. Take the median or mean from sample frames. And then the last background model that we will discuss is the Gaussian mixture models. So what happens here is that your each background point uses a mixture of Gaussian distributions. Usually you have 3 to 4 distributions per pixel. Now what do you mean by this? Okay, so for each pixel, so previously in the previous models that we've discussed, each pixel, right, is trying to compute for like one value. Okay, so what is the pixel value for this one in the background? So maybe like 1 to 7, and then this one is 1 to 3, and then this one is 50, and so on. So just one value. Okay, so it's a static background image basically. So if you have a static background image, then that is just one image, right? If you get the previous frame, that is still one image, right? If you get the mean or median from samples, you will still get one background image from that because you're computing the mean or the median. And even if you do running average, still the same thing, you're basically producing one image, right? But in Gaussian mixture model, what you're doing is for each pixel, okay, so this is for GMM. For each pixel here, if you zoom into this, there's multiple possible distributions. Okay, so it could be like a distribution, a Gaussian distribution centered at let's say 127, and then another one wherein it's also a Gaussian distribution, but this time centered at, let's say, 200. Okay, something like that. Okay, so the reason why we have multiple the reason why we're using Gaussian distribution is because we want to account for lighting changes. Okay, so if we so let me remove everything. So let's say if you have one value only, like 127, then it has to be exactly 127, right? So with the threshold, you can like have like a little margin, but really you are saying that the background pixel needs to be 127. But if you use a Gaussian distribution centered at 127, then you're leaving a little room for error, right? So if it's 127, that's fine. If it's near 127, like going here, going there, that could still be fine still, right? So because of lighting changes, like it could be slightly darker going here or slightly lighter going there, then you're accounting for lighting changes by using a Gaussian distribution. Now, why are we using multiple or a mixture of Gaussian distributions? It's because okay, we also want to account for appearance changes. Okay, so the background changes over time. So we don't just want one Gaussian distribution, we want multiple distributions. So maybe this distribution accounts for one appearance of the background, and then another distribution here accounts for another appearance of the background possible. Okay, so if you have multiple distributions, then you are robust to appearance changes, because you're not only limited to like one appearance of the background, but you can have multiple possible models of the background. Okay, so that's the reason why we have mixture of Gaussian distributions. So you can do this in OpenCV using the create background subtractor MOG method found in the BG segment module. Okay, so Gaussian mixture models deals with moving background objects like a leaf, for example. So let's say in your video, so if this is your frame and then there's a tree here, and let's say that there's a wind, right? Ooh, there's a wind. So this leaves might be moving right here. Okay, so your background could be if it's only static, then this movement of the leaves here will also be detected as part of the movement, but we usually don't want that. We don't want to concern ourselves with the moving background objects. We only want the foreground objects. So by using Gaussian mixture models, we don't have to worry about it, because what you can do with Gaussian mixture models is that it could model two things, like the leaf and the sky in the pixels distributions. Okay, so what do you mean by this? For example, so let's say right here, so let's probably zoom into the leaf right here, and then there's the sky, like there's a cloud here. So maybe it dips like way too much, such that it becomes like this at some point. Okay, and then the cloud is much visible, or the sky is much visible. So at this point here, if we zoom into this point, so you have parts wherein you're modeling the leaf, and then at times you're also modeling like the sky, right, based on the movement of the leaf. So your model is kind of prepared for both, whether it's a leaf or a sky. Then yeah, it knows the appearance of both. Okay, and it knows that it's still part of the background. So each distribution will have a weight depending on the frequency. So if the leaf part is more frequent than the sky part, then this distribution will of course have more weight. Okay, so we still consider others, but usually we go by in order of weight. Okay, so the one that has is more frequent is considered more. Okay, so what we do when we actually use the Gaussian mixture model is we try to compare each pixel to the Gaussian distributions. Okay, so if you have multiple ones, so can you match this Gaussian distribution? If not, go to the next one. If not, go to the next one. Okay, if nothing is close, then you will actually create a new distribution, because maybe this is a new part of the background model, right? But if something is close, or if it's a match, then you also update the distribution, because you've seen a new instance of that part of the background. So maybe if, let's say, your distribution kind of looks like this, like at 127, but then it matched at, let's say, 135, and it was considered a match, then maybe you can adjust your distribution to make it slightly wider now, okay, so that because you know now that 127 and 135 are both matched by this distribution, so you can extend the distribution, or you can update the distribution to accept more values like this. Okay, so you can do that by updating the distribution. And then how do we determine if it's close or not? So if it's within 2.5 times the standard deviation of the Gaussian distribution, then we consider that a match. Okay, so yeah, and it will be considered part of the background if it matches at least one of the distribution. Okay, but if it doesn't match any, then it's part of the foreground. Okay, so those are the background models. Now all of them have this set of challenges or problems, especially when we're doing background subtraction. Okay, so no matter what model we usually encounter these challenges. Okay, so first is sudden lighting change. So what do you mean by this? So for example, if there's clouds passing by, or you turn the light on, okay, so it will change the lighting instantly from one frame to another. Okay, so because of that, the background model will also change, right, abruptly, because of the sudden change in lighting. Okay, so you need to consider those instances as well. And then there's also gradual lighting change, like if you're doing a time lapse from, let's say, noon to afternoon, okay, like 12 to 4 p.m. So there will obviously be gradual lighting change. Okay, so if your background model is static, it doesn't change at all, then you will have problems, because later on your detections might be either too noisy, or it's not detecting anything at all. Okay, so yeah, you have to consider gradual lighting changes as well. And then of course the noisy foreground, like if there's shadow, shadow is also detected as motion because it's not part of the original background, right? But we usually don't want to detect shadows because we're not concerned with shadows. We're only concerned with the people, right? Or same thing with rain. Okay, so rain could be detected, okay, especially if the raindrops are like significantly big enough. Okay, so it makes the foreground noisy. If you have motion in your background, that's also a problem, like as I mentioned earlier, trees that are waving due to the wind, or sea waves. Okay, so the sea could be considered as background, but then if there's like big waves that make this sea appear to move, then you have motion in your background, which is another challenge, because you don't want the background to interfere with the motion in the foreground. Okay, so yeah, motion in the background will also mess up your motion detection. And then changes in the background also, we also already mentioned this earlier, like parked cars that are moving out or moving in also. Okay, so changes in the background, if you don't update your background model, then it would be susceptible to these problems. Moving items. Okay, so yeah, it's similar. So those are the challenges for background subtraction. And yeah, so that's it for motion detection. Now the next task that we'll discuss is object tracking. So object tracking is kind of similar to object detection, right? So in object detection, you detect an object of interest in an image. However, if you're doing this in the video, it would be too expensive to perform object detection per frame, because imagine if you have a video that's long, then obviously there will be thousands or even millions of frames. So to do that 1,000 times would be too expensive and computationally inefficient. Okay, so instead of doing object detection per frame, what we can do is object tracking, wherein we try to locate an object which is usually moving in successive frames of the video. Okay, so you track or locate the object. Okay, so in object tracking, we usually use information about the object from previous frames. Okay, since we've presumably seen it in previous frames, then we can use that information to locate it again in the current frame. So information like the appearance, okay, so the color, the size of the object, we can use that because, for example, if you've seen a green ball that's around 30 centimeters in diameter, okay, then you have an idea in the next frame that you're looking for a green ball that's around 30 centimeters in diameter, something like that. Okay, you can also use information about its movement, so about the location. So if you saw it in the top left in the previous frame, then it would be around that area also, okay, in the next frames. And then the direction at which it is going and the speed of its movement, you can also infer and learn about it. Okay, so use information about the object from previous frames. So that is obviously faster than doing detection per frame, because if you're doing detection per frame, you're starting from scratch each time. Okay, there is no information sharing between frames because your object detector will treat each image individually or independently. Okay, so there is no sharing between frames. So object tracking also helps when detection fails. So when there are false negatives in your object detection, then object tracking could help. So it can fill in holes left by detection. So for example, maybe in frame 1 you detect it, and then in frame 3 you also detect it, but you don't detect it in frame 2. So you can infer where it could have been located in frame 2. So maybe something like this. So let's say that this is your frame. In frame 1 it was somewhere here, and then in frame 2 it was somewhere here. In frame 3. But in frame 2 you don't know because it was not detected, right? So maybe you can infer like it's going here to here, so maybe it's somewhere here in the middle. Okay, so you can fill in holes that are left by the detection, so you can maybe predict that it's somewhere here. Okay, so infer where the object should have been detected in frame 2. You can also predict likely future positions based on expected trajectory. So if you have if you have detected it like this, okay, so it's going on this trajectory, so on the next one maybe you can expect it to be somewhere right here, and then the next could be somewhere right here. So you can also do predictions going forward because you have a pattern of the motion, the direction, and the speed of the motion, so you can estimate where it could land next. Okay, so yeah, you can also do predictions. Now we usually distinguish between single object and multi-object tracking. So for single object, obviously you're just focusing on one target, and then in multi-object you are tracking multiple objects, like for example multiple cars. Okay, so we also distinguish between offline and online tracking. So in offline tracking you usually have a video file. Okay, so you can do look ahead because you have access to all frames in the file. Okay, so you can look at future frames, previous frames, and the current frame. But if you are doing online tracking, that means that you are receiving a video feed, which means that you cannot look forward. Okay, you cannot look at future frames. You can only look at previous frames and the current frame. Okay, so we need to be aware of what kind of tracking we are doing, because it would be limited if you are doing online. There is detection based tracking and detection free tracking. So if you're detection based, obviously you're using a detector, and then if you are detection free, you're not using a detector at all. Okay, so most of the tracking algorithms that we'll discuss are detection free, but for detection based, you usually divide that into two tasks, right? So task 1 is object detection, so you use a detector here, and then task 2 is object association, wherein you try to associate the detections from time t to detections in time t plus 1. Okay, so from this frame to the next frame. Of course, because it's detection based, it would rely heavily on the quality of the detector, but this is not really a problem nowadays, because you have CNN detectors or ConvNet detectors that are very fast and accurate. Okay, so you can also use detection based tracking if you want to. So what are the applications of object tracking? You can use this in HCI, human computer interaction. You can use this in augmented reality, right? So in security and surveillance, of course, if you're keeping track of the crowds and CCTVs, right? Traffic control in monitoring vehicles. Self-driving cars, okay? So you're tracking a pedestrian, so that you can try to avoid them, and also other cars. Also in medical imaging and in sports video analysis, tracking can be helpful as well. Okay, so there's a lot of applications of tracking. Now, what are the challenges in tracking? First is, if you have a moving camera, then it would be difficult, because as you mentioned earlier, if you have a moving camera, then it also adds to the difficulty of motion detection, because you're not sure whether that movement is because the camera moved, or is it because the object moved. Okay, so if the detection of motion is already being muddied, or being made even more challenging, then tracking also suffers from that. Okay, occlusion. What if sometimes the object becomes hidden, right? So for example, if let's say there's a human walking, so you're tracking them. Okay, you're putting a bounding box over them, but then the human passes over like a wall, or maybe a post of some sort. So when he goes through here, you might lose the tracking of the human, because you lost him. So when he's behind this solid object here. Okay, so if you cannot see it, you might lose track of the human itself. Okay, next is identity switch. Okay, when you cross paths with another one. So what does this mean? So for example, if there's a person right here, so you're tracking him, and then there's another person here, and then they cross paths. So at the time that, like, they are almost overlapping, so person, okay, I might draw the other one in green. So the person number 2 is in green. So at the point where they are probably like overlapping already, so you might lose track of where the original person was. Okay, because once they separate, what might end up happening is that you might end up tracking the green person. something like this. Okay, so that's identity switch, okay, which usually happens when you cross paths with another similar looking object. Of course, the change in lighting and weather is always a challenge in terms of video analysis, right? So if you change in lighting, then the object that you're tracking will appear different, because let's say it was a bright green ball, but then because of changes in lighting, it looked like darker. So your object tracker might say that, hey, this is not the same object, because I was tracking a bright green ball and then it became a dark green ball. So maybe that's not it. So changes in lighting also messes up tracking. Change in shape. Okay, so the change in shape also is a problem for tracking. So maybe you're tracking a person that's like jogging. So maybe the pose is something like this. Okay, so it's running. So your tracking model is expecting a human or an object of this shape, but then suddenly he did jumping jacks. So he was doing this now. Okay, so this form is different from this one, right? So the running form is different from the jumping jacks form. So that's a change in shape. So your tracker might say that, hey, this is not the same object, because I now have, like, I had hands earlier downward, but then this time the hands are above the head. So this is probably a different object. So the tracker might consider doing that. So yeah, changes in shape can also mess up tracking. And then besides shape, there's also change in appearance. Okay, so if a person takes off the jacket or the hat, then that also kind of changes their appearance, right? So you notice how, like, in movies, when there's a chase scene, like one person is chasing another, and then to be able to lose the person that is chasing you, you kind of take off your hat or your jacket, and then supposedly that will make the person chasing you lose track of you. So similarly, the object tracker might also experience some sort of problems like that. So if you take off your jacket, like maybe the person was tracking a person, the tracker was tracking a person that was wearing like red jacket, right? So maybe the model is like, hey, look for a red jacket, but then he took off the red jacket, and now he's just wearing like sando, a white sando. So maybe something like this, a white tank top. So there's a change in appearance now, and this might also mess up your object tracking. Okay, so those are the challenges for object tracking. And there's also one last, which is change in size, by the way. So for example, if especially if they are moving towards the horizon or moving towards you, so there's a change in size. So for example, the car here, like these are the wheels, for example. So it might appear big right now, but then later on, if they go towards the horizon, like somewhere here already, it might become smaller, right? So if you were expecting an object of like this size, and then it became smaller, so that might also mess up the tracking. Okay, so those are the challenges for object tracking. So now let's see the four stages in object tracking. First, you have target detection. So this is when you actually detect the object of interest and you try to draw a bounding box around it to signify that, hey, this is your target. Then you also do some kind of appearance modeling. So you want to model the object's visual appearance. Okay, So you want to make it robust to changes in lighting, angle, occlusion, and other distortions, because you don't want it to just have like one template. Okay, so you don't want it to have like one appearance only, but then if you change in lighting, it cannot match anymore. Okay, so you need robust features and representation, so that even if you have like minor changes, it would still detect that object. And it might be useful to use a statistical model like Gaussian, for example, just so you have uh, a wiggle room, so you have room for error, and you're not doing like exact template matching. Okay, next is motion estimation. This is when you try to predict the object's future position. Okay, and then target positioning is when you actually use the approximate location to lock down the exact target's location. So in motion estimation, so earlier we mentioned that if you've been tracking the movement of the object, then you can predict that, hey, probably the next location would be somewhere around here, right? So that is motion estimation. Now target positioning is actually in the current frame, you will start at around this area to look for the actual object. Okay, so use the approximate location to lock down the exact target location. So if you're starting at the new frame, you won't start like at a random spot. You don't need to start here, you don't need to start here, because based on motion estimation, you know that it would be somewhere around this area. So you can already narrow down your starting spot. Okay, so those are the four stages or four steps in object tracking. Okay, so let's now look at the different tracking approaches, starting with the most basic one, which is exhaustive search. So this is of course just brute force. Okay, this uses template matching, and you use a template image of the object and you try to search for the best match in each frame. But as we mentioned, if you just use a template image, it's not robust to changes in appearance. So this is not very advisable to use. Okay, so the next one is called mean shift, and for mean shift, this is an iterative method. Okay, so you don't just do this one time. So you iterate through it and you use probabilities based on histograms or pixel distribution. Okay, so you start with the object's position in the current frame, and then at the next frame you will search the neighborhood starting at that position that we had. So if this is your position, let's say for example, you know that in this frame your object is somewhere here. So in the next frame, you will also start at this neighborhood. Okay, so maybe around here. Okay, so you will start search at that neighborhood because you know that your object was somewhere there in the previous frame. Okay, and then you will find the best match by maximizing histogram similarity. So you remember histograms, they are just like they show you how your pixels are distributed. So are there a lot of blue pixels or are there a lot of green pixels? So based on that, you can match the appearance or like you can match the object by trying to find the region with maximum histogram similarity. Okay, so you will actually use a hill climbing algorithm, which is kind of similar to gradient descent, but the opposite, because gradient descent is going down, hill climbing is going up. So in hill climbing, the basic idea here is if you're at this point, you would want to go upwards, wherein you would gain the most value. So this is basically a greedy algorithm. Okay, so hill climbing is greedy, so you would go upwards or go to a direction wherein you can go upward the most. Okay, and since this is greedy, it works most of the time but not all the time. So there are times that mean shift would be suboptimal. Okay, so we'll also see that in the demo later, wherein it would have some errors. Okay, so that's hill climbing. and then in CAMshift you use a fixed window size. Okay, so it's not robust to changes in size of the object. So for example, if you have, like, let's say this ball right here, so at the first frame you have you know that the ball is this size, but then what if later on the ball went backwards? Okay, so maybe there's a just to show perspective. Okay, what if the ball rolled backwards and is now somewhere here? Okay, so it's now small. So the for CAMshift it will still use the same like window size, so still the same window size. Okay, so we'll also see this later in the demo, but yeah, that's the basic idea. Now there's a variation of CAMshift which is called CAMshift, or continuously adaptive CAMshift, which updates the window size. So it's not the fixed window size, it would be adaptive. Okay, so CAMshift and CAMshift are similar, but CAMshift is more adaptive because it updates the window size. So in OpenCV you can use the CAMshift function or CAMshift function to do this. Okay, so let's see some examples of CAMshift. So here it's tracking the player in orange, so it's doing that, and then in this one it's tracking the player in white, right? So yeah, and then here in the next one it's tracking the blue ball. Person is juggling 3 balls, 2 are orange, 1 is blue, but you can see that yeah, it's still tracking the blue ball. So this one is using CAMshift. So yeah, this one is the yellow ball, and then here you have a car chase. So yeah, you'll notice that it's still using the fixed window size, so even if it zoomed out and the car is supposed to be smaller, it's still using the same fixed window size, right? So yeah, that's CAMshift. And then even when it's zoomed in and the car is supposed to be bigger, so you'll notice that the bounding box is not occupying the whole of the car because it used a fixed window size which was set at the start. Okay, so that is CAMshift. Now for CAMshift, the adaptive one, so you have face tracking here. First, this is using CAMshift, so the fixed window size. So even if he moves back and moves forward, the window size remains the same. But if you use CAMshift, okay, so now it would be adaptive. Okay, so it would be bigger if he moves closer, and then yeah, so it's kind of adaptive now. Okay, so we'll also see more demos later on in the last part of the video. But yeah, that's CAMshift and CAMshift. Next, we can also look at optical flow, which is related to tracking. And optical flow is basically computing the magnitude and direction of pixel shift between 2 frames. So if there's movement between the 2 frames in a particular pixel, an optical flow will detect that. Okay, so you can see the pattern of apparent motion of objects in consecutive frames, and this will be passed to something called the motion vector. So the motion vector is what you'll try to compute. Okay, so optical flow is usually used to guide trackers. So optical flow will look something like this. Okay, so at each pixel, probably if there's movement, then you can model that by showing how much it moved and the direction of the movement also. So there's 2 types of optical flow. You have the dense optical flow and the sparse optical flow. For dense optical flow, it's called dense because you're estimating the motion vector of every pixel in the video frame. So you're doing it for every pixel. Okay, Okay, that's why it's dense, because there's a lot of pixels that you need to compute the motion vectors of. So one example of this in OpenCV is the Calc Optical Flow Farnibach. Okay, so Farnibach's method is dense optical flow. So it would look something like this. Okay, so a lot of pixels. So you form a grid. Okay, so and in each part of the image, you're trying to detect if there is movement using the motion vector. Okay, so that is a still image. We'll see demo videos in a while, but first let's talk about the opposite one, which is the sparse optical flow. In sparse optical flow, you try to extract feature points first in the frame. Okay, so good features that will be robust to changes. Okay, and then you track the location of these feature points. Okay, so you don't track all pixels, unlike in dense. You only track feature points that were detected. Okay, so an example of this is the Lucas Canade feature tracker, which you can use in OpenCV by calling Calc Optical Flow Peer LK, which stands for Lucas Canade. Okay, so it would look something like this. So it's not all pixels anymore. So maybe you detect like corners here. So these are the corners in the plane, and then those corners are what you track. Okay, so that's sparse optical flow. And then finally, we also need to mention Kalman filters, which Kalman filter is a signal processing algorithm which tries to predict the location of moving objects based on prior motion information. So basically, what we mentioned earlier, that we can predict the next location of a moving object based on the trajectory. So it works well even if the measurements are uncertain or indirect, and it's usually used in self-driving cars and even in robots. So for navigation of robots and navigation of self-driving cars, Kalman filters are usually used. Okay, so I have a small demo here of Kalman filters. So you'll notice here that there's a blue circle, and this is the prediction of where the next location of the ball will be. Okay, so you'll notice the red ones are actual observations of the location. The blue circle is a estimation, or like a prediction of where it would appear. Okay, so that's the usage of Kalman filters. Okay, so let's now look at more demo videos, and we'll go back to motion detection, and we'll also see some tracking demos. So let's start with static background for motion detection. So for static background, so I'll go through each window first. So this is the frame here. Okay, this one is the static background, which I took from the first frame, which is actually this one. On the third window, we will get the difference of the frame and the background, and then we'll threshold it using the value 40. And then in this window, I will dilate the difference image, just so I could fill in some of the holes. Okay, so dilation will do that, and I'll do it 3 times. And then I will process the contours and only keep the contours with area greater than 2500. The reason why I did this is because I wanted to remove the small dots, as the small contours basically. So I wanted to set a minimum size like 50 by 50, so that's 2500 in area. So if you are less than 2500, then you will be removed. Okay, so it will be processed in this window here, and then this window here in the bottom left would show you the final mask and then the number of boxes, bounding boxes. So let's see. Okay, so you'll notice that in the dilate part there are some noise already, like some dots, but because of the contour area processing, we can remove those dots. Okay, so going back here, yeah, so those small dots here, if you'll notice, they're visible, but because we process the contour area, they're gone. And then now, when the person enters, okay, so let's see that. So this door here is opened, and then there's the person already partly visible, but because this part of the door, the plywood, is kind of looks similar to this part still of the background, so that's why the door part here is not detected in the difference. Okay, it's only the person and the background part. Okay, and then if we dilate it, then we get like for example, the hole here is much better looking here. And then if we process the contour area, so small what do you call this, small objects like this right here and small objects like this here are removed in the processed one, so they're not there anymore, so the mask looks cleaner, right? And then we apply the bounding boxes here, so let's play that. So yeah, it's not perfect, and if you'll notice, even the shadow was detected as part of the motion. So yeah, there, this part here is shadow, so that's that's also detected as motion. Okay, so that's because we used static background, and this video was had some okay results because we had access to like a static background image, which was the first frame, and in the first frame there really was no moving person yet. Okay, so that's why we had this like okay looking results. But what if this time we start with some objects already part of the background? So in this video, so the first frame of the video is already has cars, so we don't have like a clean image of the road without any cars, so that's why our static background is already has cars. So look what will happen. Yeah, the detection is terrible. Why is that? Because we have moving objects as part of the background image. This is a static background, right? So those are also detected here in the difference, and even when we dilate and when we do the contour area, the detection is always there, right? So this area right here, this diagonal, is always part of the detection, so it's also noisy. So that's the limitation of a static background, is when you don't have a clean background, then the results will be terrible. Okay, so that's static background. Next, what if we use the previous frame? Okay, so for this one, it's more or less the same as the previous one, but I've updated the parameters. For this one, I used threshold only of 10, not 40. I dilated it only once, and then the contour area is smaller because this video is smaller, so 625, so basically a 25 by 25 window. So let's see. Okay, so this uses the previous frame as the background, so you'll notice this one, which is the previous frame, is used as the background itself. Now it kind of detects the ball, but you'll notice that it's like blinking, so there's noisy detection. So in some frames it detects 0, in some frames it detects 3 because of the shadow here, and then no. So yeah, 0, and then you have sometimes you have 0, 3, you have 1 at times like this. Okay, and the reason for that is because in some cases the previous frame and the current frame does not differ by much, because maybe the ball hasn't moved by a lot yet. So that's why if you use the previous frame directly, then you have like a noisy result. So I tried to update this and use the fourth previous frame instead. So I don't update the previous frame right away, or the background right away. So I wait every 4 frames. So every 4 frames I change the background. So this is the result. So it's less noisier now. So there's still some blinks or some non-detections, but compared to the one earlier wherein it's always like blinking, on off non-detection, here it's much smoother, right? And that's because we kind of waited 4 frames before to update the background. Okay, and same problem here. You'll still notice that shadow was also detected as part of the motion, because, well, it differs from the frame to the background. Okay, so that's previous frames. And if we apply it to the car example, then we will do something like this. So yeah, this one is much cleaner than the static background, right? Because at least the background is always updated, and so we have like the difference between the frame now and frame 4 frames ago. So there's a significant difference in the image. So when we dilate it, so for example, those holes here are filled in, and then when we process the contour areas, contours or part of the mask, like noise, like this dot here, are removed, and we also fill in the bigger contours, and so we have cleaner detections, right? So yeah, let's play it again one last time. So again, this is previous frames. Okay, so yeah, but you'll notice there's still some noise along the curb, right? So there's like on the edge of the road are being detected. Yeah, so that is previous frame. Next, let's look at running average. And in here, I just have the frames here, and then the running average, this one is using 0.1 as the learning rate, then this one is using 0.01 as the learning rate. So this, the top one will learn fast, will update faster. The bottom one will update slower because it's incorporating new images with lesser weight. So this is running average. So let's see the result. Okay, so you don't need to look at this final boxes frame. It's more or less the same. You're detecting cars. What I want you to focus on is the updating of the background model. So at the top one, the cars are moving faster, right? Because of the 0.1. So the background model is kind of like being updated quickly, whereas at the bottom part, 0.01, the cars are fading slowly, right? And eventually you get like a clean image of the road almost. So eventually you will learn the background, which is much cleaner compared to this, wherein you always have like the moving parts, moving objects are integrated into the background. Okay, so yeah, that's running average. So their results are somewhat similar in terms of detections, right? Of course, there are still like the noisy detections of the line here, but yeah, more or less similar in terms of detection. I just wanted to show you the difference between using 0.1, which means that it is faster updating, okay, and 0.01, which means that it's slower in learning, but eventually you get a cleaner background model without any moving object. Okay, so yeah, it's running average. And then next, same thing, running average, but this time we have like another traffic video. So yeah, in point 1 you can still see like faintly the cars that are moving, and then in point 01 you have the cars that are stationary, but eventually they are being eased out, because eventually it learns that, hey, this is this part of the pixel should be like a highway color, like the gray color for the road. Okay, so yeah, that's the running average. And then next is mean and median from samples. So for this one, I just used for the top row, it's using mean from 50 samples, and for the bottom row it's using median for 50 samples. And you'll notice just from the background itself that the median's background looks cleaner, because you'll notice like right along here, if you focus on this area here, the median's road is much cleaner compared to the means here, because there's like a streak, this one right here, I don't know if you can see that. Yeah, and here there's no streaky part. Okay, and this is because we're using mean or average, so you have like consider parts of the sample images that are being combined, whereas in median you're looking for the center of the values, right? So yeah, so let's see their difference for the mean and median. Yeah, more or less the same in terms of detection, but the mean and median background is now static. It doesn't change, because what we did here is I showed you this one earlier, right? So basically what we did for this one was this was the frame, and since I'm using 50 samples, so maybe I take one here, I take one here, I take one here, I take one here, and so on until I get 50 samples. And then out of this 50 samples, I take the mean. So these are the images that I have, so I stack them together, and then I take the mean or the median of those images to produce this background here. Okay, but everything else is the same, because you're still just doing background subtraction. Okay, so yeah, and then we have another example here. This is still mean and median from samples. So you'll also notice that for some detections here, they're not really separating the cars. So for example, okay, let me find one. Okay, right here. So for this one, in one box, for example, like this box here, this one here, you actually have 3 cars, right? You have this one, and this one. And the reason for that is because the contour, or the contour is connected right here. So they're only detected in one box. Okay, so those are some of the limitations also when you're just doing plain background subtraction. Of course, you can do some morphological transformations, but you have to do it in a case-by-case basis also. So yeah, so that's mean and median. And then finally we have mixture of Gaussians from the MOG mask. So you have this one, this is the mask, and then the final mask is the one that I processed, and then the final boxes are here. So yeah, also has some good results. So mixture of Gaussians, and then let's also run this on the other car frame. So you'll notice that the initial mask is very noisy and a uh, lot of false negatives as well. But then when we process it to the final mask, like the frame actually became much better. Like for example, in this one, there's a lot of, in this one here, there's a lot of holes, right? But in the final mask, it was processed cleanly so that it could detect this scar right here. Okay, so yeah, it's MOG mask. So that's it for the demos of the motion detection. And then let's look at demos for tracking, starting with mean shift. So for this one, we'll be tracking the green ball, and in this part here, we are showing the histograms. So we mentioned that mean shift works with comparing histograms, right? So you'll notice that it's mainly green and some parts of yellow. So yellow because the ball is yellow green, right? So it will be tracking that. So this is mean shift. So it has a fixed window size, and even if the person will move backwards later on, making the ball smaller, the window size will remain the same. Okay, or if he moves forward and the ball becomes bigger, the window size will still remain the same. So now that he's moving backwards, it's supposed to be smaller, but now kind of fits already. Earlier it was not fitting. Okay, so yeah, let's just try to finish the video. And of course there are some errors, right? So like in this part here, when he raised it to his head, and then it became confused and the tracker stayed in this area, but then it kind of recovered and still tracked the ball when the ball came back to the vicinity of where it got stuck, right? So because mean shift is a greedy algorithm, as mentioned, it can get stuck in local maximums at times, which is not the optimal one. Okay, but most of the time it should work out well. Okay, so another example of mean shift. This time we're starting with this, still the same yellow green ball. So this is the histogram right here. So yeah, it's moving it around, and then there will be some errors because of or no, not yet errors, but you'll notice that here he moved back, and so the ball should be smaller, but because this is mean shift and it's using a fixed window size, it's still using this window size because the ball was initially this big, right? But then when he moved back, then the ball became smaller, still looking at the big window size, right? Because it's not yet adaptive. And then yeah, so and then when he moves forward later, it would go back to the like original bounding box size. Okay, so that's the problem of mean shift. It's that it doesn't adapt the window size for the object when it's moving away or towards the camera. So let's try to use CAMshift instead, wherein the window size is adaptive. So let's try it on the first video. So now the bounding box is not actually a box but like a circle, which is adaptive in size. So you'll notice the size of the circle change as the ball moves away also. So you'll notice that it's shifting, and yeah, the bounding circle is also like kind of updating. Okay, when he moves back, right? So it's still kind of tracking that. And basically what this is doing is comparing which region is somewhat similar to this histogram. Okay, so yeah, that's CAMshift. Okay, so yeah, that worked perfectly. But then CAMshift is not perfect even if it's adaptive. So in the second video, Okay, now he's playing it around. So the tracker actually lost the ball at some point here, right? So at this point here, when he threw it, right, the tracker stayed here because the ball was moving too fast, and now the tracker is stuck in his arm, which is weird. And then it kind of recovers, but then it loses again, and then switches back and forth from head to the ball. So yeah, CAMshift is not perfect because it's still basically a greedy algorithm, right? So yeah, but at least for CAMshift, the improvement is that we are now using a adaptive window size. Okay, and then let's look at last two demos for optical flow. So yeah, here this one is dense optical flow. So each region here, you're estimating the flow of the flow of the movement basically. And then when you combine those movements, you get like the heat map of where the movement is. So that's dense optical flow using Farney-Bach's method. And then for sparse optical flow, so first you detect feature points like this. So these are probably corners or good features to track, and then those are the only points wherein you keep track of the optical flow. So yeah, not every pixel. Okay, so that's an example of the sparse optical flow, which is kind of weird if you think about it, right? Because in this one, it's not very dense because, well, only some pixels are actually moving. But in here, in sparse, it actually looks dense because of the number of features that were being detected. But anyway, yeah, that's the difference. For dense, you compute it for every pixel. For sparse, you locate feature points and only track those feature points. Okay, so that's it for this video. In summary, we discussed the usage of video and doing video analysis, and how video is different from image, but basically video is just a sequence of images, right? So to do motion detection, you're basically segmenting out the foreground from the background. Okay, and to do that, we usually use background subtraction. But for background subtraction to be successful, you need a good background model. So we discussed several background models, starting from the static background and like using the previous frame, and then using a running average, sampling, and then getting the median or mean, and then using mixture of Gaussian models and so on. Okay, so whatever you choose for your background model, make sure that it's taking into account changes in the background over time, like lighting changes or moving objects and so on. Okay, we also talked about tracking, which is basically repeated object detections but in video. Okay, but for tracking, we actually share information between frames, so we kind of know the object's appearance and the object's movement, like location, direction, speed, and with that, it makes it easier for us to actually narrow down the choices for where the object could be located, right? So we also talked about optical flow, which shows you the direction of the pixel change, pixel movement. So it could be dense or sparse, depending on what you use. Okay, so those are the video analysis tasks that we discussed for this video. So motion and detection and tracking. So that's it for this video. If you have any questions, please don't hesitate to ask, and I will see you next time.